Other uses for X-rays and the understanding of X-rays came rapidly. In 1899, Hermann Haga and Cornelius Wind demonstrated X-ray diffraction through a narrow slit and estimated the wavelength of X-rays to be 1 × 10 to the negative 9 meters. In 1912, Max von Laue showed X-rays diffracting through crystals, which enabled the study of the structure of materials, X-ray crystallography. Both of these indicated a wave nature for X-rays. But then, in 1923, Arthur Compton showed that X-rays were acting as particles when low-intensity X-rays scattered off electrons. And we'll look at the Compton effect in more detail later. Much of quantum physics focused on the different ways of looking at light and electrons, whether they are particles or waves. We'll return to this too later. Earlier on, I mentioned that some of the experiment with X-ray tubes involved either changing the material of the anode or changing the potential between the cathode and the anode. The result of this were spectra like the one shown below. Here's a graph of how many X-rays are produced, the y-axis is the intensity, at different wavelengths, represented along the x-axis. For a target anode made up of a specific element, this type of graph is called a spectrum. It's an X-ray spectrum. As you look at this graph, what do you notice about it? When you look at the X-ray spectrum pictured below, you can see that it consists of 2 key parts. One is a generally smooth distribution and a couple of peaks. The smooth or continuous part is called Bremsstrahlung, or braking radiation. It results from the energy emitted as the electrons strike the target, losing their kinetic energy and releasing this energy in the form of light. The 2 peaks on the X-ray spectrum relate to the internal structure of atoms that make up the anode. We'll discuss this later as we talk about models of atoms. Would you expect all elements to have an identical curve with a Bremsstrahlung like this and certain peaks? As it turns out, the peaks in the X-ray spectrum are different for different atoms or different elements. Each atom has a different internal structure and consequently will have a different spectrum. So these spectra can be used to identify different elements, just like fingerprints do for people. To show you an example of real X-ray spectra and just how unique they can be, here's the spectrum resulting from a copper X-ray tube. It has many peaks, as you can see, and a higher relative intensity of the Bremsstrahlung at lower wavelengths.